We are building slowly towards the story of energy and general circulation. So I'm repeating many points. Here we are again with our meridional stream lines, stream function showing Hadley cell seasonality. And we are now going to add some meat to this repeated claim that the meridional circulation is very weak outside the tropics. So what is happening? So this is something we just saw. We said the large-scale thermal wind relation seems to hold when we just look at the zonal mean meridional section of zonal winds with the thermal winds and the geostrophic shear. But we also added that when we look at temperature and height contours on pressure surfaces, we had these eddies on them. So what's happening? Obviously, angular momentum is catching up with us, right? Angular momentum keeps increasing and becomes unrealistic. Mathematically speaking, actually, you can produce a state of just zonal flow with no meridional velocities at all to balance the energy distribution and the rotation. Okay, you can generate an equilibrium that way, but that's an idealized case and we will not bother with it. So you cosine at any latitude the azimuthal velocity relative to the rotation, which means what? In our case, it's the zonal winds, longitudinal winds, right? Is omega a squared minus a squared cosine squared. We already did this and said it's omega a sine squared phi or cosine phi. And we said cosine phi is getting smaller as we go to latitudes, higher latitudes. So poleward heat transport is required to balance the energy budget. We already know this, right? Energy loss at high latitudes, energy gain at low latitudes, and in the tropics, the overturning Hadley circulation clearly can transport heat poleward, but it terminates in the subtropics with subsidence over the subtropical gyre. We also left something open. We said if you just look at the temperature distribution, it's fairly uniform in the upper atmosphere, and the air is moving from subtropics into the tropics, so it's not obvious, or intuitively you can say that it's probably not moving thermal energy, right? We'll have to add something else nonetheless. How do we transport heat beyond the Hadley cell if there is no strong meridional circulation? This is the reason why we have been looking again and again at this meridional stream function figure, right? Everyday observation tells us that picture in the mid-latitude atmosphere is not one with purely zonal winds, but actually it is highly wobbly and full of these storms, in fact. Right? So this purely zonal wind figure, which we have repeated so many times, saying mid-latitude westerlies, is actually wrong at the surface at least. Okay, in the upper atmosphere you find strong jet stream, which is used by airplanes, for example, to as tailwinds to zip along much faster, but it's not really true near the surface. And near the surface we are worried about weather prediction all the time. If it was such a steady, nice westerly flow, you could just predict the weather very easily by seeing what's coming down the pipeline, right? Obviously that's not possible because we produce this axisymmetric model and then we put the subtropical jet right there without saying anything so far about why the Hadley cell actually terminates where it does. And as I already alluded to, we actually don't have a very clear answer yet anyway. So if you are thinking about doing a PhD, there is a very nice problem to work on. Show why Hadley cell terminates where it does. Okay, so the main point we will add here is that the extratropical atmosphere is hydrodynamically unstable because of this angular momentum problem. So looking at our thermal winds again, what did we do next in this experiment? we simply started ramping up the rotation rate of the tank. This was rotating at about 1 RPM, less than 1 RPM. 1 rotation per minute. That is really, really slow. Actually, it's 0.95 rotations per minute. But we did that just to produce, you had 1 RPM and then slowed it down a little bit to produce thermal winds. We did that just to demonstrate the concept of thermal winds, and we increased the rotation to, I think, about 10 RPM. We can keep increasing it and produce more eddies like this. So this was the beautiful baroclinic eddy in the lab. What happened here? We still had ice water in the middle, warmer water outside, so we had the pole and the equator, so we had a nice thermal gradient just like we have on Earth. We increased F, we increased the rotation rate, and that's equivalent to going from the equator towards higher latitudes on Earth. What happened? Instantaneously, the flow went unstable. Hydrodynamic instability is something like this, where warm water from outside is flowing in, cold water from inside is going out. So you have this nice, you have something like 6 waves here. I think you can count 1, 2, 1, 3 maybe, whatever. Right? So this is what the eddies are. They are mixing cold polar air with warm subtropical air. And what has to happen is there is something called an eddy flux. So we will see what that is. That has to move net energy across the latitude lines from lower latitudes to higher latitudes. This is all. Okay, the equations get very hairy. The hydrodynamic instability equations get kind of complicated, but nonetheless, if you look up Holton, you will get a good idea of what they are. But we will get a good idea here as well in a heuristic sense. Okay, so this is our main concept of baroclinic instability. Here we increased F by increasing rotation rate. On the real Earth, you just move from the equator to higher latitudes, so we increase F, Coriolis. That's all. Okay, so angular momentum conservation breaks down when F becomes too large, and that's our good old equation. Okay, cosine phi in the denominator, so the amplification by R, distance from the local axis of rotation. This is an important concept, but for you to remember, it's very simple. You just say angular momentum conservation breaks down, so system breaks into eddies, and that's hydrodynamic instability. And if you can derive that expression for angular momentum with the cosine phi in the denominator, you are gold. You're good to go. Okay, that's one of the big concepts for this baroclinic instability idea.